Today, we're going to be talking about the Bayesian heart of neural networks. What does that mean? Hopefully, you'll find out very soon. And this is also going to be, hopefully, a practical introduction to deep learning, also for people who have never done deep learning or have always been curious about it. Hopefully, this will help people. And little spoiler alert, you're going to be training your first neural, maybe not your first, but you'll be training your own neural network by the end of this hour. So let's get started. So like I mentioned today, hopefully, for sure, not hopefully, we'll be defining and training our own neural network using a framework called JAX, and also an associated framework called FLAX. And the practical problem that we're going to be looking at is we're going to be building this neural network to classify different stars by type. And finally, Sebastian will give a probabilistic interpretation of neural network training. OK, so let's start with a question. So for people who've never seen Slido before, all you have to do is point your phone to the QR code, and then you can actually vote on this poll. So everybody, please vote. I do not know how many people have voted, so I will just give people 30 seconds. So the question is, say that we're classifying between two different star types. Say they're called type 1 and type 2. That's not real, but it's fine. And our training data has 80% type 1 stars and 20% type 2 stars. So that basically means if you have 100 examples to train from, 80 of them are type 1 stars and 20 of them are type 2 stars. So if that's the case, and then after training your model, then you want the model to predict some kind of classification for a star that's actually type 1. So what do we think the model is going to output in this scenario? Do we think it will predict type 1 with 50 to 80% confidence, 80 to 100% confidence, or type 2 with 50 to 80% confidence, 80 to 100% confidence, or do we think that the model is just going to implode because it's too confused by the fact that it's not a balanced class distribution? OK, actually, I just realized that you can see the number going up. So a lot of people have voted. Thank you so much for voting. Let's see what people think. Oh, OK. So most people, oh, sorry, I can't read. 52% of people think that the model will predict type 1 with 80 to 100% confidence. Someone just updated their vote. That's cool. And OK, so most people seem to think that it's going to predict type 1, but it's not super clear to people what confidence level the model is going to have about the prediction. So that's really good. And I also, yeah, thank you for humoring my stupid joke that I came up with at midnight last night. OK, great. So we're going to be coming back to this. Hopefully, in Sebastian's segment of the talk, the answer will become clear. Great, thanks. OK, so here's a bit of context about the actual concrete problem that we're going to be looking at. So we're going to be distinguishing between these different star types. And for non-astronomers in the room, here's a very brief introduction about stars. This diagram is called a Hertzsprung-Russell diagram. And basically, all it's showing is plotting stars based on their luminosity, so how bright they are, and also their surface temperature. So you can see that once you look at stars in this structure, or in this plane, some pretty cool structure occurs. So there's this little island of stars called white dwarfs here that are kind of lower in luminosity and also less, or this is more hot. Then this main sequence of stars is sort of where most stars live their lives. And for example, our sun is here. So it sort of makes this diagonal line across this luminosity temperature graph. And then there's a little branch here that we call the giants. And then up here in the very high luminosities, very bright star area, there's this region called supergiants. So there's this nice distinguishing between 4 different types of stars that is shown basically on this plot, and that's pretty much what we're going to be doing. So we're going to have a data set of stars. The information we have about them is all of them. We know the luminosity, and we also know their temperature, and then based on those 2 values, we're going to try to differentiate which of the 4 types these main types of stars they are. Also, I forgot to say this, but feel free to ask questions whenever. OK, so what about this neural network component? So there are 3 key ingredients to building a neural network. First, you need a training data set. So we sort of already touched on this with the Slido question. But a training data set basically consists of the data x. So in this case, x is the star temperature and magnitude measurements. So for us, it's like a tuple of just 2 float values. And also the desired outputs y. So for us, this would be the known label of the star type. So is it a white dwarf, a main sequence star, a red giant star, or a supergiant star? And just for the fact that, because we're working with numbers, we just encode them as integers between 0 and 3. So 0, 1, 2, 3 corresponds to these 4 types. Of course, if we're talking about neural networks, we actually need a neural network model. And in our case, we'll be using basically the most sort of basic of these neural network classes, which is called multi-layer perceptron. So it only has 2 layers, or ours maybe has 3 layers. But basically, it's just a bunch of matrix multiplies and some nonlinearities. Feel free to read up on neural networks on YouTube or something if that part is kind of still hazy. And finally, we need a loss function. So what do we actually want to train the network to be able to do? So the loss function is defined such that minimizing this loss function leads to the desired behavior. And basically, in English, that means predictions should approximate the true value. So if you want it to be able to distinguish between these star types, then hopefully the predictions at the end of training are going to be pretty similar to the actual star type that we know it is. So in our case, we're using a loss function called categorical cross-entropy because we're doing this multi-class classification, so classification between 4 different types of objects. And there's more to come about loss functions and how we choose loss functions and things like that. But basically, the concept of a loss function is just, what should this network actually be able to do well? And of course, the next very practical concern is, we hear about all these different machine learning frameworks out there. There's JAX, there's also PyTorch, and there's TensorFlow. There are probably more, but I think these are the main ones that people mainly talk about these days. Which one should I choose? And my personal answer is that I think any of them are fine. I personally use PyTorch, but today we're using JAX because JAX has all these nice features, and apparently JAX equals love. I think it's actually JAX equals XLA loves autograd. I just realized that literally just now, standing here. I thought it was JAX equals love, and then all these were just little pictures on the side. OK. OK, so what does it actually look like to write a neural network in JAX? So here is sort of a basic, minimal viable product version of a neural network. And we're going to go through it little piece by piece. So first, we have to define our actual neural network. So I mentioned before that this is called a multi-layer perceptron. So we just abbreviate it using MLP. And then all you have to do is subclass this flax.linen.module class. And you basically write what you want the network to do into the call function. So here we're doing a dense layer with 128 neurons. And then you pass that through nonlinearity called a ReLU. And then you do a final dense layer to bring it to, in this case, we're just bringing it to 1 neuron. So maybe we're doing regression or maybe binary classification or something like that. And of course, once you define the class, then you have to instantiate the class. So pretty straightforward. And then, so these are basically just big matrices. So we have to fill these big matrices with some numbers. So usually we fill them in with some random numbers. There's a lot of complexity in terms of how to initialize a model. But for now, we're just saying, initialize it with some random numbers with the size and shape of the input that we expect. And there's also something called an optimizer that will help you basically define how to update the model weights as a function of the gradients on the loss function. So how the model like how the model parameters will actually evolve while the training is going. So the optimizer that we're using here is called Atom, which is a very common choice these days. Next, we've moved on to the loss function. So again, this is like what metric should the model optimize for? And then in this case, since our model output is one-dimensional, then it's kind of like a binary classification type situation. So we're using something called binary cross-entropy instead of categorical cross-entropy. I know it's just a lot of words, but basically binary cross-entropy is like if I predict a 0 and you predict a 1. If the truth is a 0 and I predict a 0, then that's good. And if the truth is a 1 and I predict a 0, then that's bad. More to come on the loss function. And finally, once you compute the loss function, then you have to update the model parameters using the computed gradients on the loss function. So that's basically handled by jax.grad is computing the gradients, and then you compute the updates on the model weights with optimizer.update, and then finally you just apply the updates to the model parameters. Any questions so far? Okay, so now it's your turn. Please either scan this QR code, which will take you to it on your phone, which would not be ideal, or you can type this into your computer. So this is actually a Colab notebook, which is, if you've never used Colab before, is very much like Jupyter Notebooks, but they run on their own hosted runtime. So we've put together this notebook for you guys to go through, and there are some areas with missing code. So I've actually written what you're supposed to write into the missing sections up here. So when you get to those points, there's big stop emojis. So it'll be very clear when you need to fill in the code. And this is the code that you need to fill in, basically just the model definition, which is an MLP like I was showing you earlier, as well as the loss function definition, which is this second method here. So feel free to play with the notebook on your own computers. We will probably have around 20 minutes to go through that on your own, and we'll just be here / in the front / milling about, answering questions and helping out with people who are having trouble with the notebook. And sorry? I think it's in, wait, I wrote it, didn't I? I think it was 10 to like log Kelvin, right? Log base 10.
Yeah, log base 10 of Kelvin.
Yeah. I saw that too when I was looking at the data for the first time, and I was like, what's going on? Yes. Okay, finally, there's a little section in the middle that says stop and await further instructions. So if anyone gets to that point, feel free to raise your hands. But yeah, I'll turn off my mic and people can start working on their notebooks / asking questions.
I think if you got -0.7, it's probably the luminosity you're printing.
You can put it against the wall.
I tried to put it here, but then it fell over.
Against the wall. Usually that's what it stands. I have a question actually about how you define in Flax the network.
Yeah.
How big is your input? Where is the output? I couldn't really understand.
Oh yeah, it's very smart actually. So it's figuring that all out by itself. So this call function is like this NM compact wrapper. When you first call the model, which is what that like initialization function does, it'll see the shape of the inputs, and it'll initialize this matrix multiplication to be the right dimensionality with your first call. And then here, it's just, this is returning a function. What it really means is that you conduct one matrix multiplication, this just function on all the outputs,
Mm-hmm.
and then you conduct another matrix multiplication and output that. And so it's like an almost linguistic explanation of what you want the model to do, and then Flax does all the hard work of actually initializing an architecture that can do those things.
Okay. So it's not as visible as you have it in PyTorch, where you have linear this and then.
I think it's very very similar to PyTorch, right? And then dense
is just linear.
Linear,
just
yeah.
yeah.
So that's your first hidden layer,
Yeah.
and then your activation function.
Yeah.
Okay, I see.
Yeah.
And then the last one is your output layer.
Yeah.
Okay.
Exactly.
Yeah, see here it's going for, so you specify at the beginning all the hidden layers, how many hidden layers you want. For dimensionality in the hidden layers, make a dense of that dimensionality.
Yeah.
Okay.
And then it's just looping on that.
Yeah. So in the code, the input for hidden layers is
The model is specifying like the how to interpret the parameters, and then the parameters are the actual thing that that gets altered. So JAX is very functional programming, and so it's returning to you like a new set of parameters, but the model is not being changed with each function call. And so those things are separated from each other. And it's a little confusing, but it also has some like great strengths in that you could hold many parameters in memory at once and plug them into the model alternatively, and it'll always behave exactly the way you expect it to.
Yeah, that makes sense. That's a good explanation.
Yeah. So you circle around and see if people have. Thing, the compute loss. Yeah, this is this is also a matrix essentially, although an array in this case.
It's just the dimensionality is number of examples and correct class.
Yeah, exactly. It's a number of examples, number of classes, because this is like the log of the probability of each class. This is the number of examples times 1, because the label is just 0, 1, 2, 3, and then this will turn it into like a one-hot encoding of that.
It can't just infer the number of classes from the labels.
It could, but yeah, it might not be in the label set. So then you could accidentally provide something that doesn't have the largest label number, and then the next time you call it, it all breaks. So it's good to tell it ahead of time what the actual number of classes is. Yeah.
Does NLP not need infrastructure?
Oh yeah, this was like I was just mentioning this to Sebastian like earlier today. Yeah, so basically, I think if you have an init function that doesn't do anything except for like call self dot whatever equals whatever, then you can do it using this syntax up here. So basically, the syntax above the nn.compact thing is the init function. but it just says like self.num classes equals num classes, self.hidden layers equals hidden layers. Yeah.
I'm just getting an error because it's telling me there's an unexpected keyword argument, which is num classes.
What version of Python do you have? Python 2 or Python 3? All right, just super quick, guys. Hopefully some portion of you have made it to the step where you have to stop and await further instructions, although nobody raised their hand as we asked, but that's okay. So the next thing is we're going to do some small modifications to the data. So we're going to explore what happens when we corrupt the data in different ways and see how the classifier changes. So we've labeled this by the side of the room you're on from your side. So left is this side, middle is this side, and right is that side. So each one of you is going to get a different corruption. Either you scramble the temperature feature, you scramble all the features in the middle, or you scramble the luminosity feature. And we're going to see how the classifier behaves on that scrambled data. So yeah, after you've seen that stop, scroll to the relevant section, and then run that section and see how your classifier changes. All right, so hopefully most of you guys have had a chance to run the notebooks and your subsection of the notebooks. So in the interest of time, we're going to push forward, but feel free to keep playing with those notebooks in the future. So at first, we started by doing this classification task on what looks like a very nice representation of an HR diagram, where everything is very nicely divided. And then, depending on what section of the room you were sitting in, we showed you a slightly harder problem. Some of you did luminosity or temperature scrambled, so it now is a lot harder to distinguish between the classes if I had taken away the colors from this diagram. And some of you did a version of the problem where everything was scrambled, and likely found that the classifier could not perform very well on a problem where there is essentially no information. But the story doesn't end there. So let's call this our easy problem, our difficult problem, and our impossible problem. So on the easy problem, you found sort of the computer scientist's dream performance for their neural network, which is that it classified essentially perfectly, right? Here I'm showing you the name of the class, main sequence, supergiant, giant, white dwarf. And on the x-axis, we have the probability it assigns on average to that specific class. So for main sequence, the highest probability is main sequence, 97%, 99, 95, 98. Looks really nice. For those of you that did some version of this slightly more difficult problem, you found slightly different behavior. So now there's still like a clear diagonal element. In particular, for the temperature supergiants, they're still really well classified. But some of the other classes are not as well classified. So for example, here, giants is almost as likely to be classified, is more likely, to be classified as a main sequence star than it is to be classified as a giant star. And that seems like a failure mode. If I take this threshold of like 50% and I assign the highest likelihood class, all of my giants, or the vast majority of my giants, are going to be called main sequence stars. And for those of you that did this activity, you probably saw something like that emerge. And then on this impossible problem, now I don't really have any meaningful difference in the classification between the different classes. So that makes sense, right? I've scrambled all the information. But maybe some of you were really alarmed by the first column of this, which is that despite the fact that I've destroyed all information and my classifier now has no idea which class each one of these things belongs to, it is assigning the most probability to main sequence stars every single time. And so if I pick the highest probability class, every single time I would say it was a main sequence star based off of this threshold. In the notebook, we draw from the probability distribution, but the most likely class is always main sequence. So what's going on here? First, let me ask you a quick question. Based on what I showed you here, do you think the classifier is biased? So take your favorite definition of bias, pull out your phone, fill out the poll, and we'll see what people think. Oh, shoot, it's already showing you the answer, people say. All right. OK, so we have 20 submissions. Feel free to keep guessing as I talk. But it looks like by a very slight majority, and please no one change this as I'm saying my sentence, more people think the classifier is biased than not biased. But also, it's very close to evenly split. So I don't know if that's because I told my friends to vote for what they thought was the wrong answer on the poll, or if there's some subsection of people who legitimately think that this is an unbiased classifier. Hopefully, by the end of this talk, I'll convince you that the correct answer is no, that there is no bias in this classifier. But let's explore that a little more in detail. So the first thing is, if any of you guys checked what the actual distribution of classes was on this training set that we gave you, the most common class in the training set is main sequence stars. And that's very believable, right? If this was a HR diagram that I observed from the sky, it's the most common type of star. So if I'm building a data set out of the observations that I have, my most common class should be main sequence. But what if I had redone the activity I just showed you, where I artificially made sure that every class was represented equally? So now I have the same number of main sequence, supergiants, giants, and dwarfs in my training data set. So originally, remember, I have these like sort of three cases: the really easy problem where I have this beautiful diagonal, the harder problem where my diagonal starts to break down, and the quote-unquote impossible problem where I had this weird overrepresentation of the main sequence. So I trained the exact same classifier on the same data. On the easy problem, I get almost perfect agreement. So it's learning the same basic mapping as it did for the previous data set. On the slightly more challenging problem, I have a similar behavior. So I still have like a nice diagonal element, but there's been an interesting flip. So for example, here, giants was predicting more often as main sequence than it was predicting as giants. And now with my new balanced data set, the giants actually have switched to predicting more often as giants. And ironically, main sequence stars are now predicted more often as giants than they are main sequence stars, which might seem pretty surprising. And then on the impossible task, I now have what most of you who said yes probably thought was the quote-unquote unbiased performance, which is that the model is now predicting for every type of class that it has about even probability of being any of the classes, which is to say it's realized correctly that it has absolutely no idea what's going on because all of the information has been scrambled. OK. And yeah, if we look at the top column, just highlighting that again. So just to summarize and hopefully get you guys engaged for what we're about to present, when the problem was easy, the classifier predicted the right class essentially every single time. And it seems like the classification was independent of the ratio of objects in the training data set. So those are the two things I'm going to want from my classifier. I want it to be right, and I don't want it to depend super strongly on the ratio of objects in my data set. As soon as the problem got hard, that broke down. First, there were certain classes where the classifier was consistently predicting the wrong class. So if I was using it to make some kind of decision, I might be quite alarmed. But even more alarmingly, the actual predictions of the classifier were strongly dependent on the ratio of objects in my training data set. And so I imagine that if I want to use this for science, this classifier is worthless because it's not really consistent in its predictions in terms of the mapping between luminosity and temperature to the class. It's going to depend on the specific training data set that I showed it. So let me ask you one more question, which is, what might solve this problem? And I've given you 4 options. These are like what the scaling bros, as they're called, would answer. Either make the network bigger or train it on a bigger data set. And then I've given you 2 other options if you're feeling a little more adventurous. There is no solution, or there is no problem. Go ahead and start responding. All right, we've reached the 20 response threshold. OK, so here are the answers that we got. So a small plurality of folks said that there was no problem. I appreciate your vote of confidence. Nope, just kidding. A small plurality of folks said that we should train on a bigger data set, so the scaling bros would be proud of you. We just needed more data. Some folks thought that we just needed a bigger network, so as the network gets bigger and more complicated, it's more expressive, and maybe the current network just wasn't expressive enough to capture this more complicated distribution. Some people said there is no solution, which would be a very boring end to the talk, but I appreciate the confidence. And then some X plurality of folks said that there was no problem at all. And obviously, I'm going to try to argue here that there is no problem at all. So first, let's ask the question, what is it that we actually want our neural network to learn? So the argument here is that we want our neural network to learn to predict the probability of a star class given its temperature and luminosity, right? In words, that's what the task that we're trying to get it to accomplish. What that really means is that I have some sort of network outputs, which are like a probability for each class, and I want it to match the true distribution of the probability of a star class given my temperature and luminosity data. This actual distribution we want to predict, right, if you went to Dave's talk about an hour and change ago, is called the posterior, which is itself a product of 2 terms, a likelihood and a prior. So the likelihood term is saying, how well does the star class determine the data? The more deterministic the star classes of the data, the more constraining this term is going to be on the probability of a class given the data. And the second term, the prior, it
encodes the information about how likely I think I am to see a star of a certain class before I've even looked at its features, right? So there's a combination of two pieces of information that go into my posterior. And this is just a slight simplification of Bayes' rule over here. So I showed you guys sort of two cases. One we called like the easy case. The other one we called the hard or difficult case. And the argument here is that actually the difference between these two cases is how important these two terms are. So in the easy case, if I look at my data in the feature space, it's really easy to tell which class it belongs to by plotting it on this 2D grid, which is another way of saying that the class of star is really deterministic of where it falls in this parameter space. On the other hand, on the impossible problem, it's essentially completely scrambled. And so even if I know the class, I don't really know where it's going to fall in data space. All classes are equally likely to fall everywhere in data space. So my information about what class it is entirely based off of my prior understanding of what class it was before I ever looked at the features in the first place. And so I'm going to pitch to you that when I say a problem is easy, what I mean is that it's likelihood dominated. And when I say that the problem is hard here, what I mean is that it's prior dominated. So let's go back and put some concrete numbers to this. So we played with two data sets. One data set where the main sequence was the most common. It was 40% of the data. And the other types were 20% of the data. And some other data set that you didn't have in the notebook that was more balanced. So every class was 25% of the data. On the easy problem, which was likelihood dominated, my two classifiers behaved identically. They gave me this really nice diagonal. And that's what we expect, because this, which is my prior understanding of the distribution of classes on my data set, plays no role. My place in parameter space is really constraining about what class I have. On the quote-unquote hard or impossible problem that was prior dominated, there, the ratio of classes, or the prior understanding of what class you're going to be before I look at the features, is entirely deterministic of what class I'm going to predict. And so now what before looked quite alarming actually lines up really nicely with the distribution of classes in my training data set. So main sequence here is predicted 40% of the time, not because the classifier has discovered some underlying truth about main sequence stars. It was 40% of my training data set, and the other ones were 20%. And here, everything is predicted roughly 25% of the time because they were 25% of my training data set, whereas the features can tell me absolutely nothing about those objects. And so the argument here is when the problem is easy, the posterior is dominated by the likelihood, and the prior of my training data set becomes irrelevant, right? Really, my posterior is just equivalent to this likelihood term, and I get sort of the dream performance of my classifier. When the problem is hard, the posterior is dominated by the prior, and the prior in the training data set becomes really important to what my classifier is going to output, because my posterior is determined by the prior. So it's not that the classifier was ever telling us anything wrong. It was always giving us the posterior. And on the easy problem, the posterior was likelihood dominated. So when I switched out the distribution of the data set, it didn't make any meaningful difference. On the impossible problem, the posterior was prior dominated. So when I switched out the distribution of the data set, it made a huge difference on what my model was predicting. And in the cases in between, it sort of interpolates between those regimes. OK, so yeah, sorry. Any questions on that, which is like the sort of central argument about what these classifiers are actually doing under the hood? So you're all convinced that there was no problem and the model isn't biased? Yeah.
OK, so I think whether or not you interpret the model to be biased strongly depends on whether you think that the data that you're training on are truly representative of the underlying distribution.
Yeah.
Like if the data sample is biased
Sure.
in a way that doesn't reflect the distribution, then you're
Sure.
going to get this behavior, and obviously you have a prior that's incorrect.
Right.
Isn't that
So
what bias means?
yes. So there's two parts to the argument there. So the first is I collected a data set that I don't think is the prior I really have about my understanding of the world. So if that's what happened, there's a very nice solution for that called importance sampling. And we have a little slide at the end which essentially encourages you to bother your favorite CCM affiliate on how importance sampling works. So it is true. You could, of course, collect a data set whose prior is not really what you wanted to enforce. And then you have to do a little bit of extra math on top of your classifier after you've trained it to get it to express the prior you actually wanted to enforce. But the separate question is, like, if I believe my data, then this is the right choice of posterior. It is like the variational inference fit to what the likelihood times prior distribution is. Does that answer your concern? Okay, at least enough that you don't have follow-up. Oh, sorry.
It answers the functional concern. It doesn't answer the existential one. You can go on.
Okay. We can talk about your existential concern after. I'm happy to. Is there a question back there?
Thank you. So I'm a stand programmer, and I haven't written a neural net before, but I know that in my stand program, I'm used to having an expression or series of statements that I can point to and say, and this is my likelihood.
Yeah.
And then I have another series of statements where I say, no, here's my prior.
Yep.
And I'm looking at this
You're saying,
code.
I never said a prior
saying,
anywhere. I never said a likelihood
yeah,
anywhere.
Exactly.
Why did it ever learn a posterior?
Yeah.
That's a great question. Save it for 2 slides from now.
Okay.
Anything else? Okay. All right, so let me address that question, which is a really good existential question. I've just sort of started asserting that we learn the posterior, but why did the network learn the posterior? I certainly never told it that. It seems I never told it that explicitly. And the answer to your question is we bamboozled you. The whole time, that's exactly what I was telling the network to do. So what do I want? I want my network to learn to match the posterior, right? How do I get 2 distributions to match each other? Well, the bread and butter tool is to say, I'm going to take their KL divergence, which is an object I know will only give me 0 when these 2 distributions match. So my loss function that I really want is the KL divergence. And you could say that secretly what I'm doing is like variational inference. Well, the KL divergence is just going to be a sum over samples from my distribution of the negative log of my variational thing, the network output. There's another term in there, but we can drop it because it doesn't depend on the thing we're actually trying to teach, which is the network. So this is the object I would want to have if I was using this KL divergence philosophy for how to train my network. Okay, our network is predicting a categorical distribution. What is the KL, the negative log likelihood of a KL distribution, of a categorical distribution? It is the categorical cross entropy, which is the function we had you guys all write when you were choosing your loss function for this neural network. And so the argument here is that the reason the network has learned a posterior is because the loss function that we enforced was exactly the loss function you would enforce if you were trying to match your network's output to the true distribution, the posterior. And then the samples that we trained the network on were samples from this posterior distribution. And so what the network implicitly learns is how to match the distribution you're giving to the underlying posterior distribution of the data, which means that all of these steps, the likelihood and the prior, they're defined implicitly, the prior by the data set you've provided, and the likelihood by the mapping within that data set between classes and features. And so the network is learning both things bundled up. And so once you have that posterior, if you want to get back out the likelihood or get back out the prior, you'll have to do some extra work. But that's what you're getting the network to learn. That's what you're incentivizing it to learn with this loss function. And so oftentimes people will say things like, oh yeah, categorical cross-entropy, natural choice for a classification problem. And the reason it's a natural choice is because it's the loss function that gets your network to output the posterior. In the end, we didn't choose a random loss function. As Helen alluded to, we chose the exact loss function we needed to get our model to perform the way we wanted it to, which was to give us the posterior, our underlying object of interest in scientific inference. Okay. So let me just conclude and then take any questions we have in the last minute and change. So hopefully today I convinced you that and Helen convinced you that you built a nice neural network with JAX. Congratulations to everyone who never did it before on doing it for your first time. Hopefully we've also convinced you that training a neural network is secretly Bayesian inference in the sense that what you're training the network to do is to predict the posterior of your parameter of interest on the input features of your data set. And because of this, our training data set defines our prior. And as I alluded to in one of my other answers, if you want to correct these priors after training, if you had a data set whose prior you disagree with, all you have to do is ask your favorite CCM affiliate about, we're not in the CCM, so we're not putting work on ourselves, about importance sampling. And you can, there's a lot of really nice work and very clean work that shows that this posterior distribution that your network is outputting can be transformed into a different posterior distribution with a different prior. So you're not married to whatever prior distribution was baked into your training data set at the get-go, as long as you're thoughtful about what your network is outputting. And that's it. Thank you.
So we actually have about 10 minutes for questions.
Oh, nice. Oh, hey, sorry.
Can you talk a little bit more, in spite of not being CCM, about this importance sampling?
Yeah, it's...
Don't you just need to look at the output vector and like multiply it by ratios of prior I want to prior I had?
There you go, you got it.
Oh, okay, so you don't have to like retrain the network.
No,
or
yeah.
reweight the network or anything.
You are, I mean, that ratio is you reweighting the network, right?
I guess the last neuron gets reweighted.
Yeah, the last output you're effectively reweighting. So it's entirely a post-processing step. There's no need to do it. There's no need to retrain anything. You could do it during training, but that's like a whole other can of worms we could talk about. Yeah. Any other questions? Yeah.
So I'll be that guy who has more of a comment than a question.
Great.
But I just want to point out that I'm in CCB, and sometimes in biology we talk a lot about like, would you rather miss a true positive or a false negative, and potentially like class imbalance has a lot to do with that. Like if you're trying to diagnose a disease, would you rather miss somebody who truly has that disease, or would you rather tell somebody they have it when they don't?
Yeah.
Yeah. So yeah, that's all.
I didn't quite understand the comment, but I think I can pivot into saying something knowledgeable myself.
I think it's more about like, this can be a problem. Like,
yeah. So I mean,
Yeah.
so I think that discussion is really interesting, but it's more a discussion of the threshold that you impose on your posterior, and so it becomes a little less important in that framework exactly what the posterior is telling you, because then you're sort of making decisions based off of that distribution, and your decision function is the object of interest, if it's fair to say that. I think here we're thinking more about it in a framework where I'm not making a call like, do I tell this person they have a disease or do I not? I'm thinking about it more like a Bayesian, where I'm trying to understand the true like distribution of classes of this object that I'll never get to check what its class is, but I want to understand distributionally what its class is. Is that a fair response to that? Yeah, that's a nice comment though. Yeah.
So I have limited experience building neural networks, and one of the things that I come up against a lot is that you need a very broad range. Like there's some really good heuristics and things that you go to for default right at the beginning, like the atom optimizer and categorizational cross entropy.
Yeah.
But like really knowing that, like what is the scope of fields and the different tools that you can use to build up your neural network, which almost seems like an art at some point.
Yeah.
Is hard. Do you have any advice about going through those, or like building up that kind of toolkit?
Yeah, that's a good question. I don't know, Helen. Do you have any? Do you want to come in with a very intelligent answer to that good question?
Can I just repeat your question to make sure we're understanding? I actually couldn't see who. Okay, I see. I couldn't see you from sitting here, but okay. So you're basically saying like there's lots of like different, like not only are there lots of like different data types, there are like lots of different architectures that are good for different data types, and there's also different optimizers, different loss functions, like a whole suite of like different sort of like tools that you learn about, and then you slot into your toolkit, and then you're like, how do I build up my toolkit, and how do I decide which tool to use at which point? Is that a good summary?
Yeah, it kind of like, as you said, as you were saying at the last part of your talk, that like we chose the correct thing because it optimized for this. How do you know that that was the correct, like, what are the basic things that you know? Like kind of like learning a language, right? What is the right word to use?
Yeah, I mean, I can give at least a partial answer to like the different data types, and then like certain architectures are like designed for certain data types or whatever. So like for this example, we used this thing called a multi-layer perceptron because we knew that we had these like two float values, and then we could just learn some kind of function on these two float values, and we don't really have to think too much about what that function is or what kind of like biases you're baking in, because you're kind of just saying like, okay, learn some kind of function of these values. But in fact, like most of the time, at least for us in science, we have different, we have like images, or we have like time series or whatever, and like certain data types or certain architectures like more specialized towards certain data types. So I guess for the example of images would be like there's this other thing called convolutional neural networks, and like one pretty cool thing about it is that it preserves some kind of spatial information. So you can be like, well, first of all, preserve some kind of spatial information. So you have this like 2D thing, your image. You kind of want to be like, well, this thing was in the top left corner. I don't want to just shoot it towards the top right corner or the bottom left corner or like some random place in the image. For people who aren't super familiar, CNNs have this sort of like window of, we think about it as a sliding window basically, where you have these weights and then you basically slide it around the image in like a snake pattern and compute weights on those. So not only is that super important, but the other, the spatial thing super important, but also the other reason why people like using CNNs is because of the fact that this window does something called weight sharing or parameter sharing, which means that the same set of weights is being slid over your image. Whereas if you were to do like the MLP approach with an image, then you would be flattening out this potentially very large image, and then you would have to have like a connection between the each individual input and then whatever like hidden layer dimension. So it can be like millions and millions of parameters in your first in just your first like set of connections. So this weight sharing thing means that you only have like a very small number of weights, and then you kind of just like slide those weights around. So there's like computational concerns, and also like concerns about or not concerns, but like if you understand that your data has like the spatial component, you can be like what kind of an architecture could possibly preserve those things. So it's partially just like, I don't know, sort of knowing the type of data and then being like, what kind of thing would make sense? So for example, this like posterior thing is like, maybe you want to do variational inference, like what kind of a thing could allow you to do that? But yeah, maybe Sebastian has more.
I think that was a very good answer. I would just, like, the only thing I do is a slight rephrasing in that, like, you want to pick the architecture that has the biases that you expect from your data set. So as Helen really nicely just described, like the convolutional network has this bias that when something appears in my image, like a structure, like a face or a cat or something like that, it doesn't really matter where exactly in the image it appeared for classifying it as a cat or a face. And that's a nice property of the convolutional architecture. There are like transformers, which have this like permutation invariance. The MLP has like no symmetries baked into it. So I think part of it is just figuring out what the symmetries are of your problem and choosing an architecture that's really good on those symmetries.
It was more of just a general question of like, where would you learn about these symmetries of each one of these?
Oh yeah.
Because I had learned this stuff, but like all of a sudden there's a million things out there that you could find. Like, what are the good resources?
No, there's definitely like a fire hose of different architectures.
And optimizers and and all these things. So.
Yeah, I don't know if we're going to have the best answer for that. I mean, the CCM folks are definitely a great resource, or just finding what other people in your field are using for that problem.
Okay.
On from that question, how would you optimize for the best loss function for your data set or task? And I was a little bit confused, or I got a little bit lost towards the end. What was the connection between the KL divergence and the cross entropy?
Oh yeah, that's a great question. So the KL divergence, all it's doing is saying, I want this distribution to match this distribution. When I enforce that, this is the loss function that I get out. The thing is that I didn't tell you what Q was, what the distribution Q I'm actually fitting is. And that's the answer to your question, which is, for this problem, I wanted Q to be a categorical distribution, which just means I'm assigning a probability to each class. And when I plug in the categorical distribution, I get something that looks like this out on the right-hand side. And that's why that was the loss function I used. Another example would be like I want to predict like a variable, like regression. And so I want to predict Q as a Gaussian with some mean and variance. Turns out that the loss function you get out looks exactly like mean squared error. So a lot of the natural choices that come from like the machine learning literature can be expressed in this way, as like you pick your distribution, you plug it into this equation, and now you know what your loss function is on your right-hand side. I think we're almost out of time. But yeah, thanks.
Let's thank our speakers.